In this video, we are going to discuss about the voltage divided bias circuit. So on the completion of this voltage divided bias, the students will be able to study the basic circuits using this diodes and the transistors. And this voltage divider bias, we know that is in the input region, the voltage gets divided. So we call the resistors as R1 and R2. So here in this biasing, we can be taking three resistors, which is called as R1, R2 and emitter resistance, that is RE. So from this resistance R1 and R2, which is acting as a potential divider, which gives the fixed voltage to the bias. So if collector current, whenever there is a change in the collector current due to change in the temperature or change in the beta or any other parameters, this emitter current will also increases, so that the voltage drop across this resistance also increases, thus by reducing the voltage difference between the base and the emitter. So due to this reduction in the base emitter voltage, base current and the collector current gets reduces. So when we can say that there is a negative feedback which is existing between the emitter bias circuit, so this reduction in the collector current will compensate us for the original change in the current. And also you can see the circuit analysis. So you can apply the KVL along the input loop along the, that is, base region as well as the collector region. So if you are considering the base circuit along this figure, that is voltage across R2 is the base voltage VB, while you are applying the voltage divider rule, that is VB is equal to R2 of I. So divided by R1 into I plus IB plus R2 into I of into VCC. Whenever there is an increase in the current, that is I is greater than IB, then you can write the equation as, that is, I is very greater than IC. So you can apply this value, that is applying the KVL along the collector loop. You can consider the collector column as shown in the figure, that is voltage across R can be obtained as the V is equal to IE RE minus VB minus VBE. So that from that we can equate I is equal to VB minus VB divided by RE. So whenever applying the KVL to the collector current, VC is equal to VCC minus IC RC minus I RE. And you can see the simplified circuit of the voltage divider circuit. So you can take this R1 R2 in the terms of Thevenin's. So to simplify the circuits, that is we take the value of voltage VT. So RB is equal to R1 parallel R2. Here also we can apply the value of the KVL along the input loop as well as the output loop. So this is the simplified circuit structure. So from this we can write that is RB is nothing but R1 parallel to R2. So if two resistors are connected in parallel, then we can write the equation as R1 R2 divided by R1 plus R2. And then this VT is the Thevenin circuit. So here we can apply the KVL. So what you will get means VT equal to IB into RB plus VBE plus IE into RE. So from this equation you can see the term, that is IB is the common term. So from this equation IB is common, so you can take the IB term outside. So VT is equal to VBE plus RB plus RE into IB plus IC into RE. So from this equation we are calculating the value of VBE. So you can take the VB term to the left hand side and other terms to the right hand side, so that you will be getting VB is equal to VT minus RB plus RE into IB minus IC into RE. So here we know this voltage divider circuit also, here we are using this to maintain the stability factor as constant. So if we maintain the stability factor as constant, then there will be the proper linear amplification in the signal without any distortion. So if any distortion occurs, it can be either lead to the cutoff region or it can be go to the saturation region. So based on these biasing methods, we have been finding out the collector current value, and as well as that is we are applying the KVL along the input side, that is base circuit as well as the collector circuit, and we are finding out the value of the current. If there is any change in the temperature, then we are making the voltage drop to make the stabilized to make it as a stabilized output. Thank you.